this talk, I will present the paper toward hardware-aware dialog systems. So let me start off with some background. So we know that retrieval-based dialog systems are memory and time-intensive. For instance, ideally, the candidate search should be exhaustive, which means that we should look through all of the responses in our response set. And ideally, our response set has to be huge so that we can address a wide range of different dialogues. These problems are even more accentuated when the system has to be deployed on embedded devices. But how do we perform the candidate search? Well, we have what is called a scoring model. So, for instance, it can be a dual-encoder model, which is like the one you can see here. So, say the user engages the system with a new utterance 1. Then we have a context encoder model, which can be something such as a pre-trained transformer or a recurrent neural network. So with this context encoder, we obtain a context embedding. And then similarly, for each response in our response set, we use a response encoder model and we obtain a response embedding. And then we perform some sort of operation between the response and the context embedding to obtain a score. This operation can be something such as a dot product. Now, one thing to notice here is that utterance 1 and utterance 2 have no interaction before their dot product. So one thing that we can do to save time is to pre-compute all of the response embeddings. However, the process remains demanding due to the huge number of responses in our response set and to the number of operations to perform. So what we propose is this architecture. So on the left, we have our database of responses, but instead of individual responses, we have clusters of responses. Now, say the user gives us a new input sentence. What we would typically do is we would run our scoring model of this input sentence against all of the response candidates. What we do instead is we use a filtering mechanism called the cluster identifier that allows us to select a subset of responses to look into, and then we use the retrieval model on this subset only. So this will allow us to have an accelerated candidate search and also is suitable for hierarchical storage solutions due to the clusters. But how do we form the clusters? Where first off, we train a similarity notion metric in this way. So we first extract n true pairs A and B of sentences that belong to a same conversation, and then n false pairs A and B from different conversations. And then we train a model on the binary task do S1 and S2 belong to the same conversation or not. And this is done to promote a conversation locality property, which means that sentences that are likely to belong to the same conversation will be deemed as more similar by this model. Next, we can compute a similarity matrix using the model that we just trained. And then we can execute spectral clustering on this similarity matrix and obtain a labeled training set where the labels tell us for each sentence which cluster the sentence belongs to. And then on this dataset, we can train a cluster identifier model that, given a sentence, will try to assign it to a certain cluster. Now, for each new candidate response, we can obtain the most probable cluster by running this cluster identifier model, which will give us the probability for each cluster, and then we assign the response to the cluster with the highest probability. In a similar way, when the user gives us a new sentence, we can select a subset of clusters via the cluster identifier and then only look into these clusters. So again, this allows us to accelerate the inference process because we only need to look into one or a few clusters. And it's also suitable for hierarchical memory solutions because we can deploy the different clusters based on the probability assigned by the cluster identifier to different hierarchies of memory. Now let's look at some results. So CI is our solution with the cluster identifier model, whereas KM is a k-means baseline, where we form the clusters by using the last hidden states of the similarity metric defining model, which is the one that we trained on telling us whether two sentences belong to the same conversation or not. So accuracy is denotes the accuracy in identifying the cluster that contains the ground truth response, whereas R at 10C denotes the recall at 10 within the cluster, which means the percentage of times that the correct response is identified among the 10 responses from the same cluster once the correct cluster is chosen. Whereas the response at 10A is the percentage of times that the correct cluster response is identified among 10 candidates, where the 9 wrong candidates are chosen from all possible responses, as opposed from the correct cluster. And we can see that recall at 10C is always lower, which indicates that the responses within the cluster are more similar or related to each other, which makes it more difficult to choose the correct one, which is what we expect, because we wanted the responses within a certain cluster to be more likely to belong to the same conversation. So it's more difficult to decide which one to select. Last thing, look at the locality and the speedup. So the locality denotes the average number of contexts per cluster for each conversation. So if it's higher, it means that during a certain conversation, we don't have to look into a lot of different clusters. And indeed, for the CI solution, this is always higher. The speedup also scales well, even though it doesn't scale as well as the k-means solution. So this means that the clusters are maybe a bit less evenly distributed. However, overall, we can still obtain a nice speedup, which will allow us to have an accelerated candidate search. And due to the locality, we can deploy some hierarchical memory storage solutions, which will let us deploy these systems on devices that don't have as much computational resources as typical server solutions. Okay, that is all for the presentation.